Hello students, welcome back to the lecture series of rotational dynamics. Again today we will start with a question. You can see the question on the screen. It has been given that we have a ring whose mass is m and radius is capital R. There is an axis passing through the center of the ring and perpendicular to the plane of the ring, and the moment of inertia of the ring about this axis is mr square. We have been asked to find out the moment of inertia about one of the diameters of the ring. So to solve this question, we need to use a theorem of rotational dynamics called as perpendicular axis theorem. So in the last lecture, we studied parallel axis theorem, and today we are going to study perpendicular axis theorem. Perpendicular axis theorem. And what does this perpendicular axis theorem say? Let us see. Before going towards this theorem, we need to have a look at the conditions that must be satisfied to use this theorem. Conditions that must be satisfied to use this theorem. So the first condition that must be satisfied is that the body, it should be a planar body. The body should be a planar body. Planar body. The second condition, we should have three concurrent axes. We should have three concurrent axes for the body, of which two in plane of the body, and one perpendicular to the plane of the body, So these are the conditions that must be satisfied before we start using perpendicular axis theorem. Okay, so let's first have a look at the statement of the perpendicular axis theorem. It states that for a planar object, the moment of inertia about an axis perpendicular to the plane of the body is sum of moment of inertia about two mutually perpendicular axes in the plane of the body. Now, for your reference, I've drawn a diagram on the left-hand side of the screen. As you can see that we have a planar body of a weird shape, and there are three axes. All three are concurrent: z-axis, y-axis, and x-axis. Z-axis is perpendicular, and xy axis are in plane of body. So perpendicular axis theorem simply states that the moment of inertia about z-axis will be nothing but the sum of moment of inertia about x-axis and moment of inertia about y-axis. So this is the mathematical statement of the perpendicular axis theorem. Now let's try to prove this, because they ask these derivations in the 12th standard board exams. So let's try to prove this. Okay, so I've made a template ready that simplifies the derivation of perpendicular axis theorem. And let's have a look at this template and try to understand the derivation of perpendicular axis theorem. So we have a planar body on the left hand side. There are three concurrent axes, z, y, and x. Z perpendicular to the body, x and y in the plane of the body, as you can see from the diagram. Now, what we have done is we have considered a point mass dm at point P. So this is the point P, and I've placed dm over here. Now dm is at distance y from x-axis. It is at a distance y from x-axis. So moment of inertia of that mass, of the complete mass of the complete body about the x-axis, can be written as integral y square dm. Now, the mass dm is at distance x from the y-axis, and therefore moment of inertia of the body about y-axis can be written as integral x square dm. Now, why I can write this? Because for point particle, we know that the moment of inertia is mr square, where m is the mass of the particle and r is the distance of the particle from the axis of rotation. Over here, we have replaced that m with dm and the other variables x and y. Finally, we just have to integrate, because dm is a very small mass, and to find out the moment of inertia for the complete body, we will have to integrate the small moment of inertias for the small dm masses. Okay. Now, similarly, this point mass dm is at a distance r from the z-axis, and therefore I can write down Iz is equal to integral r square dm. Okay, so the equations that we have got till now is Ix is equal to integral y square dm. Moment of inertia about y-axis is equal to integral x square dm. And moment of inertia about z-axis is equal to integral r square dm. But if we have a look at the diagram, this is a 90-degree angle and we have a right angle triangle where we can write down r square is equal to x square plus y square. And if we substitute it in the formula for moment of inertia about z-axis, we get integral x square plus y square whole into dm. And if we separate the integrals, we get integral x square dm plus integral y square dm. And Iz is equal to integral x square dm is nothing but Iy, and integral y square dm is nothing but Ix. So finally, we have Iz is equal to Ix plus Iy. Iz is equal to Ix plus Iy, which is the mathematical statement for perpendicular axis theorem. And this is the proof. This is the proof of perpendicular axis theorem, which you can write in the question if they ask the derivation for perpendicular axis theorem. So Iz is equal to Ix plus Iy. Now, let's get back to our question. We have a ring whose mass is m and radius is r. About an axis passing through the center of the ring, the moment of inertia is mr square. We have been asked to find out the moment of inertia about one of its diameter. So what I can do is I can take the vertical axis as z-axis, the horizontal one I can take y, and the slant one I can take x. Now, as you can see clearly that x and y axis both are nothing but the diameters of the ring. And therefore, if we walk about any diameter, the ring is going to look same. And therefore, the moment of inertia about x-axis and y-axis is going to be same. So I can write down Ix is equal to Iy because the ring is symmetric about its diameter. And I can use the perpendicular axis theorem because the conditions are satisfied. The ring is a planar body, yes. Then I have three concurrent axes, yes. One is perpendicular, yes. Z-axis is perpendicular. The other two are in the plane of the body, yes. X-axis and y-axis are in the plane of the body. So I can easily use the perpendicular axis theorem. So I can state Iz is equal to Ix plus Iy. But since x-axis and y-axis are both diameter and the ring is symmetric about its diameter, Ix is equal to Iy. Therefore, I can write Iz is equal to 2Ix or 2Iy. Therefore, from this equation, I get Ix is equal to Iy is equal to Iz by 2. And from the diagram, we can see that Iz is nothing but mr square. So mr square by 2. So now we can easily answer the question that moment of inertia of ring about any of its diameter is mr square by 2. So in this lecture, we have derived and proved the mathematical statement of perpendicular axis theorem. And using that, we have also solved an example and found out the moment of inertia of ring about any of its diameter. Thank you very much.